Okay, yes. Ansh, can you tell me if the rays after getting refracted, okay, rays after refraction, if they actually meet, they truly meet, what sort of image will you get? Yes, Ansh.
I don't know.
Okay, Michelle, answer the same question. After getting refracted, the rays are meeting.
A real image?
Okay, their real image, and will they be uh, upright or are they going to be inverted?
Inverted.
Real images are always inverted. And if the rays are not going to meet after getting refracted, those are called, and we just try to do back tracing. Yes, if we are obtaining it by some back tracing concept, then they will be called as virtual image, and virtual images are upright, or you can also write the word erect. This is very important because whenever you do your ray diagrams, they always ask you all the nature of the image. So what is this combination? These are called as nature of the image, whether it is real or virtual, whether it is inverted or upright. Okay, that has to be very clear to you. Now whenever you have the concept of virtual, so how can you identify it's a virtual image? So whatever lens you are taking, it can be convex or concave lens, we'll see the conditions and all, but just giving you an idea that after refraction you see the rays are going away. Okay, you can see one is going that side, the other is going downward, they are getting diverted, so they are never going to meet. So where will they meet? If you want to make them meet, they will meet on the other end, that is this side. So the orange dotted lines is something you have made so that you try to make them meet. But on the right side, literally, they're not going to meet. Such type of images are called as virtual images. So always think virtual images like a piece of a triangle. Okay, if I cut the triangle horizontally, which is parallel to the base. So what we will do, we'll just erase the top portion and forget about the bottom base also. So you see that the bottom part of the triangle, they are going away from each other. But where will they meet? They will meet here at the top portion. Okay. So this is how you need to know for some images and their conditions. Okay. Now we come to the diagrams and their rules. Okay, so if I take a convex lens, okay, I take a convex lens. Anushka, tell me, the first focal point will be on the right side or the left side? The first the focal point, sorry, will it be on the right side or the left side?
Left side.
Okay, and the second one will be on the right side. Okay, so here will be your f1 and here will be your f2. This is for the convex lens. Okay, so the first, all the rulings we will do, the rules will be similar much to the convex and concave. Now, the first rule is that suppose the light is coming through, the first one we'll take it for the optical center. So I take a line which is cutting through the optical center. It's a straight line that goes through the optical center, and this is your O. O is optical center. Now, now we have seen all that it's actually getting refracted, but we just consider and neglect that little lateral shift that it is going through. So anytime rays are falling and going through the optical center, it will go straight, it will go undeviated. No matter it's coming from the top or it's coming from the bottom, that doesn't matter. If it is passing through the optical center, it will go undeviated. That is the first rule. I'm not giving you the statements for the rule. We are only going to do the concept clearing here. As I've said, it's a very lengthy chapter. Then to include all the definitions will not be possible, and it will consume a lot of time. So for that, the notes have been already given. We'll just understand it, how to use them in the diagrams. Same thing will be applicable for concave lens. So I have a concave lens here, and I draw a straight line that should pass through the optical center. Okay, and let me mark this yellow point as the optical center. And same thing, if the rays are going to fall through the optical center, that it's coming from anywhere, it will go undeviated. So whatever rules we do for concave, similar things will go for convex, apart from just the point of discussion whether we are taking the first focal length, first focal point or the second focal point, that will differ for both. So maybe the diagram will look different, but the rules are same. By statements, they are same. So this is the first rule: you take concave lens or convex lens, and if the incident ray is passing through the optical center, it will go undeviated. If you want just a short line, I can give it to you, or you can simply draw this. No need of proper construction. Roughly, you can draw this and write a statement. If incident ray passes through optical center of the lens, so it can be any lens. That's why I've just generalized and written lens. It will get refracted undeviated. Okay, quickly write this point. Yes, finish with the writing and the diagram, everyone. Anyone is still writing any point? Okay. Now the second condition. So if you take a convex lens and you have a principal axis there, the rule we are going to just see. So for convex lens, f1 is on the left side and f2 will be on the right side, and this is your optical center. So if you take any ray incident such that the ray is going to be parallel to the principal axis. So it's going this way. Yellow is the principal axis, orange is the incident ray. Orange and the yellow line, they are parallel to each other. So if such is the incident ray, it will get refracted such a way that it will pass through the second focus. So where it will go through, it will go straight and it will get bent, and that ray will pass through the second focal point. Okay, this is for convex lens. How is the incident ray? Incident ray is parallel to the principal axis, and if it's such, then after refraction, it will pass through the second focal point. I'm just directly writing F2. Then writing and the diagram, so turning from left to the concave lens.
Ma'am, is it different for the concave lens? Or
Yes, the diagram, the condition is same, the statement goes same, but it looks different for concave lens. So in case of concave lens, suppose this is how you're going to take it. This is your concave lens. This is your principal axis. So where does the F1 and F2 lie? For concave lens, where is F1? To the right side or left side? Yes, Adit. Concave lens, F1 will be on the left side or on the right side, where it should be. First focal point, second focal point. Where
Right.
should it lie? Yes, first one will be on the right side and second will be on the left side. Okay, so the thing is, of course, the light is coming parallel, but it is parallel to your principal axis. Same thing that we have seen there. But because the concave lens has the characteristic property that it will try to divert the rays. That is, after refraction, instead of making it come to the focus, it will divert it. It will make it go away. Okay. Now, so you can take one more parallel line or incident ray from the bottom. That will also give you the same result. Instead of going or in getting inclined towards the focus, it will get away from it. That's how is the case of concave lens. But then we do the tracing back, right? So we will trace back a line such that we will use a dotted line to always use dotted line, something that you are doing from your own end. Back tracing always needs to be done with dotted lines. So you're going to take this ray and make it go through the or pass it through the F2. This way also on the bottom one that I have taken, you're going to take this ray and make it pass through F2. So the pink one, which is the dotted ray, is something that you have drawn. This is called as back tracing. So they are not actually getting or they're not meeting at the F2 point. They're meeting um, at the other end and going away from the focus. But we try to make it meet at F2. So it appears as if it is coming from the F2 point. So let's say if somebody is going to view from this end, there is some viewer, so many rays coming from here. So let's say one single ray has reached this eye. So for this eye, the light is not coming parallel. For this eye, the for that is how it is getting delusional, right? So for eye or for the brain of any animal or human, for it it's as if it's coming from this F2, because for us light travels in a straight path. So but really the light is traveling parallel and then it is getting deviated. But for a viewer from that end, let's say A is a viewer, for him that light is coming from the F2. So this is how the figure will be for the F2 and F1. So of course, because F2 and F1 will be at different places they're located, so the diagrams will look absolutely contrasting between convex and concave. So you can see this. I'm not taking the bottom one, so don't get confused. You can take some extra lines, that's okay, but I just made that to make sure that lines can also be taken below the principal axis. So this is how it looks like for convex. Okay, now we go to the next rule. So the next rule is for ray which is actually coming through the focus. So if you're taking a convex lens, okay, you have this is the principal axis, and this is your f1, this is f2. Now the ray is technically, just need to get it close. This is f1, this is f2. So this ray is actually coming incident, it's falling on the f2. So as it hits the lens, it will get refracted such way that it will now start traveling parallel to your principal axis. So for convex, ray is passing through the f1 and then such a way that it will get refracted and emerges out parallel to your principal axis. Okay, and for concave, if you take, so this is your principal axis, this is f2 and this is f1. So in this case, the ray is going to, of course, come from the focus. Now, which focus? The ray will always come from the left side, even though the f1 is, sorry, it's f1. Even though the f1 is on the right side, you are not going to be taking any incident ray on the right side. Incident ray is always by default taken from the left side. So the ray is going to fall such a way that as if it was going to go through the first focus, but it is not going to. It is going to get deviated. So as it hits, the pink line that you see is the actual refracted ray. And you can put this part in dotted lines. I'll just redo this. This is your principal axis. This is F2. This is F1. Okay, so you take a ray that is supposed to look like as if it's going to go through the F1, but it's not actually coming from there. It's falling like this. And the way it is getting refracted, the true refracted ray, that will go parallel to the principal axis. So pink is the incident ray, blue is the refracted, and the dotted white line that you see is the trace back that we have made. So in case of concave lens, it's of course going to emerge out parallel to the principal axis after refraction, but how it is taken, it's not coming from the focus. It is as if it's just directed to that first focus. So this white dotted line is the extra work that we have done. So whichever lens you're taking, the concept is after refraction, the ray will emerge out parallel to the principal axis. So these are the three basic rules we should know when we do the diagrams, the ray diagrams. So first is, if I sum up and just put the rule, the first one was very easy because the diagrams looks very similar, identical. So concave or convex lens, if the ray is passing or falling on the optical center, it will pass out undeviated. That's about the optical center. It will go undeviated. Second condition, if the rays are parallel to the principal axis, it will go through the focus point. It will get directed to the focus point. In case of convex, every time you have to do that back tracing because it gets diverted away. You will have to do a back tracing and make it meet at the second focus. And the third one was about light that is falling on the focus, then it will go parallel to the principal axis. And in case of convex, it's little different. You have to draw a line as if it is falling on the first focal point, but it is not falling. We have to do a dotted line. How it is technically going to happen, it will fall and it will go parallel to the principal axis. So these are the rules whenever we are going to take the concave and convex lens. Okay, now today we will only focus on the convex lens diagram. Okay, concave will not give you a lot of conditions. Concave lens have very limited conditions for the diagrams. So only two conditions are there for concave. One is when you keep it at infinity and then you take any other position, it will give you a fixed result. So today we will only take concave lens diagram. So now write the heading, write ray diagrams. And we are taking the first lens, that is convex lens. Done writing the heading. Okay. Now I'm giving you all an idea that I already told you. You can do it with measurements so that you get exact result. For now, you can just roughly draw it. Later, after the class, you can cover up with proper measurements. Now, whenever you do diagrams, there is no need of actually drawing objects like tree or a person. Okay, there is no need like that. You just have to beat any object. You're just going to use arrow mark, and it is headed towards top. And if you're getting an inverted image, okay, this is object. Image, if you want to show it is inverted, it will go downward, where the arrow mark that you see will be on the bottom side. Clear? So for any object, you will only use arrow mark, and the image of that object will also be the arrow mark. Okay, now let's first take few conditions. So you all can roughly draw a convex lens. You can use scale only for the principal axis, and for the ray diagram, you can utilize a scale. So we will take a principal axis, mark, we need the focus. Focus is what we want. So F1 you will take here, and F2 you will be taking here. Okay, and you can also mark O for optical center. Yes. Done writing, everyone? Now we will begin with conditions. Now I'll just first tell you all the patterns that is mandatory, and this is the same thing you will do for your exams. Whenever you draw the structure, towards the end, there are few things you should always get a practice of it. Even if they have not asked you, when you get a practice of it constantly, that will also help you for the numericals. Okay, so once your diagram is done, like you have done your diagram, towards the bottom end, you will mention basically three things. First is position of object. Where did you keep the object? That is the position of object. So it can be at infinity, at first focal point, between center of curvature, wherever you have placed it, you have a location for the object, you will write that. And in the same manner, first is position of the object. Second is where did you obtain the image? So that is position of image. Where did you found the image with on the screen? So that is the second thing. And third thing is related to the nature of the image. You always find nature of image. You never find nature of the object. So it all has to be written as nature of image. Now what is nature of image? We have just learned the combination real and inverted, or virtual and erect. This is your third point. And yes, one more point. Fourth point will be the size of the image. Size. Now, size can also be replaced with the term height. Okay, it means the same. Size does not means the lateral width, like is it fat or thin? No, size here means the length of it. That is, if this is like around 4 centimeter, you got the image 8 centimeters, so it's double of it. So it is in terms of height. It is never taken in terms of width. So size of the image. So while writing that, you can, if the size is bigger, you will write enlarged. Okay, if it's too small, okay, very small, you will use the word point size. I'll tell you all these things. Point size means very, very tiny. You can't even see it. It is forming, but you are not able to see it. So point size image. And if it is a tiny image, like if it is 6 centimeter and you got the image 2 centimeter, you can see it, you will use the term diminished. And which is to, instead of point size, there is another word you can use. Instead of point size, you can use the term highly diminished. Highly diminished means you are actually telling them it's so tiny that you can't see it. So point size can also be replaced with the keyword highly diminished. Diminished means smaller size. Enlarged means bigger size. Some books, I think, they instead of enlarged, they have used the term magnified. That is also fine. These keywords can be replaceable. So enlarged or magnified means the same. Okay, and very big. So you will say highly magnified or highly enlarged. So these are related, these keywords are related to the size of the image. So these four things will be there whenever you write the information about after your ray diagrams, because most of the time they do give you this part that you are supposed to write these information. Okay, so after every diagram, these 4 points, the pattern will be fixed that you will be considering. Okay, now coming to the first case. So first case that we're going to take, you can all write case number 1. You can write on the top instead, so that, and when you get time after the class, you just make it with double line. You can underline the cases. So case number 1 is when the object is kept at infinity. Cases are always depending on where did you keep your object. Position of the object always forms the case. So object is kept at infinity. So when object is kept at infinity, in case of convex lens, where will you get the image? That is what we are going to find out. Okay, now my first question, if you all remember the first lecture, I had given you a hint point that whenever the object is kept at infinity, it's actually not in true sense. It does not mean that it is out of the galaxy and it is at a very infinite place. No. Infinity is according to the focus of that lens. Lens is thinner, so for it, a longer distance, some kilometer distance from where at least light can fall on it, will be considered as an infinite distance. So that distance is related to the size of the convex or concave lens. It is not in true sense for human that infinity means somewhere out in the galaxy, somewhere at a particular distance. Now, object at infinity, I gave you a condition. So my question is how the rays are going to come from an infinite position. How you recognize, okay, these rays have come from infinity. What is the way to recognize these rays? Yes, anyone? Yes, Ansh. Rays coming from infinity, how do you identify them? Ratio.
What if they meet at a point?
No. Michelle.
They are parallel to each other.
Yes, that is right. They are parallel to each other. See, not necessarily they are parallel to the principal axis, but these rays are parallel to each other. I can take rays coming from the top, and yes, I can take rays coming from the bottom also, or else rays which is parallel to the principal axis. This way also they are parallel to each other. So the rays which is coming from infinity, they will always be parallel. Now, how you make them parallel, you're taking the top portion, bottom portion, or just parallel to the principal axis, totally depends on you. There is no mandatory rule here that you should go by what the textbooks have given that it's coming from the top portion, inclined and coming from the top portion. So you can also take rays coming this way. This is also parallel. The two green lines are parallel to each other. Okay. Now, if I know the rules, what is the rule stating for convex lens? If rays are parallel to principal axis, where they should meet? Yes, where they should meet after refraction. Yes, Anushka.
At F2.
Yes, they will meet at F2. So I will make two lines because there are two rays. Mandatory two rays has to be there. You can take more than that also. But as I said, more the rays you're going to take, it's just going to become more, clutter on the diagram part. So where are they meeting? Wherever the two rays are intersecting after refraction. Orange rays are refracted rays. Green are the incident rays. So you have to see where they are getting, um, intersected. Okay. So rays are kept at infinity. So they are parallel. And where are they meeting? At the focal point. Now, what things do we get to know from this? So let's write all the information. You all can roughly draw this, and then, as I said, point-wise you will write the same thing. Position is already the case that we are writing. Position of object. Where is the object? It is kept at infinity. Second, where is the image formed? Wherever you see the intersected point after refraction. So position of the image, where is it getting intersected? F2. So you will write at and mention it which focal length. You can also roughly write focal point, and focal plane is also fine. Now when will you write focal plane? I'll tell you if I'm changing the situation. But for now I can write at second focal point. Now understand this thing. You can directly write focal point. Okay, need not specify second focal point. We will practice this till the time you're very sure that, okay, for convex lens, every time when I say focus, which focus should you consider? You will be considering the second focus always. Okay, Second focus will be the default focus for convex lens. Okay, so when you write an exam, instead of properly writing like this, like second focal point, that will also be right. They're not going to give you incorrect. You can also write it as at the focus, because we understand, as in when we get good at practicing the focuses, we get to know that okay, when I say focus for convex, it is second focus. Okay, so these two done. Now let's discuss the nature of it. Okay. Now, for now, we do not know whether it is inverted or not, but most of the cases that we have for convex lens, the nature is it is always going to form. They're actually meeting, correct? Let's first go by that. These rays are actually meeting at focus, so they are real. And how are real images? Real are always inverted. Real images are always inverted. That comes your third point, which is nature. And then you will write the fourth point. Fourth point is the size of the image. So if it is exactly lying on the principal, because focus point means it's on the principal axis. So the size is highly diminished. As I said, you can also use the other keyword, which is point size. So you can write it here, highly diminished. Also, you can write point size. So four things related to all the diagram is done, and even the diagram is also sorted. So this is the first case we have taken. Quickly, let's revise up. Object which is kept at infinity, rays coming from there will always be parallel to each other. And parallel rays, if I've taken in this way, the parallel to the principal axis, so they are meeting at the focus point. So technically it is the second focal point. So position of the object, position of the image, how is the nature and the size of the image, these 4 points separately you have to write down after the diagram. So take a note of it. And also I'm going to make a little change in this infinity concept, just to make sure that need not that the lights coming will always be parallel to the principal axis. Additionally, wherever your F1 lies, you will be having your C1, and wherever your F2 lies, you will write your C2. In many books, C2 is also written as 2F2 and 2F1. We will speak about that once this is done. Yes, anyone is still taking a note? Finish writing. Okay. Now we discuss about the replacement of C with 2F. So if I just take one curve and let's say this is the center, correct? And this is actually the radius of whatever curve path we have taken. So this is center. We call that a center of curvature. It can be 1 and 2. It can be any term depending on the lens I'm taking. I'm just taking half part of it. The point between these two has been taken as the focal point, because the point that we're taking is from the optical center. Let's say this is F1. So if I see this is point A, this is point B, and this is point C, whenever we consider the F and the C, AB and BC will be equal in their measurements. So what is it? AB and BC, they are equal. And AB is referred as the focal length. We write focus with capital F and focal length with small f. This is also very important to note. Focus point, that point you are going to note, that focus point will be with capital, and focal length. Length is from the optical center till focus point, that is the focal length. That is considered with small f. So this AB is the focal length, we write f. And we got to know that AB and BC are equal, that means BC can also be referred as F. But when I see into the figure and I try to add this length AB plus BC, that's actually giving me the center of curvature. I'm writing C1 there. So AB is F and BC is F. F plus F will become 2F. So any time center of curvature can always be replaced by 2F, and this F will be capital F. Okay, this F is going to be capital F. So center of curvature can be written as twice the focal length. Okay, and if you do not want to confuse, you can also write directly C1 or C2. And if writing 2F, so you have to write it as 2F1 or 2F2. Because sometimes in some numerical questions, they give it in this way that, what is the length of 2F2, or what is the length of 2F1, or sometimes they give you in terms that the object was kept between 2F2 and F2. This way they can give you, or they can say the object was kept exactly at 2F2. So what is this 2F2? You don't have to worry. That's nothing but they're speaking about center of curvature. If it is 2, so C2. If it is 1, write C1. Okay. So these are some terms that because every book has a different way to explain. So they may use some other terms. You don't have to get confused there. Okay. Now we do have another condition. This is still the case 1 I'm taking. Case 1, but I have this convex lens. Okay, and this is the principal axis. This is the principal axis. Now, instead of taking, like this is again the same object at infinity, what I will do is I am going to consider that the rays are somewhere coming from the top. So I'm writing 2F1 here, and this is F2 and 2F2. Okay, the rays are coming from infinite position, but it is going to be coming in such a way that they're parallel to each other. So I'll take a ray. I will take this ray, which is going to first come. I have to take two rays, and these rays should be something that my rules will fit into. So I'll take one ray that will pass through the that is optical center. So of course I know it will go undeviated. So let it go very straight like that. And I will take a second condition where the ray is parallel for sure. Ray is parallel to the green ray, but it is passing through the F1. So Nidhi, tell me, when the ray is passing through the F1, what should happen? Should it go straight? Should it pass through F2, or should it go parallel? The ray is incident on F1.
It'll go parallel.
Yes. So after hitting here, that is, it comes like this. Okay, I don't have the measurements correct, so this is just a rough figure. It will go parallel to the principal axis after hitting. So this is the point where they are meeting. Okay, the rays are going to meet. So there are two rays that you see. The green rays, they're parallel to each other. They are parallel. That means that they are coming from infinity. And the first ray, I can see it's passing through the optical center, so it will go straight undeviated. And the second ray that I see is passing through the F1. So after hitting onto the lens, it will go straight. Straight means it will go parallel to the principal axis. And this is the point that they are going to meet. If I would have done with the correct measurement, technically, this point that they are meeting is nothing but falling on the F2. It's not exactly on F2, but you will notice that it will fall. I try to use a dotted line, okay, like this, maybe red color. Okay, and I will make it pass through that line. So you can clearly see this is the point of intersection. Let me call that as A. This A is at such a point that if I try to draw a straight line, It is passing through F2. So this means that it is somewhere falling on the line of F2, not exactly on F2, but on the line of F2. So in this case, I will say that it is the image is formed on the focal plane, not exactly at the focus point, but somewhere on the focus plane or focal plane. Okay, so this is also something that you can try. That the rays are parallel. Yes, they are parallel because they are coming from infinity. But according to the rule, the first ray is passing through optical center, it will go undeviated, and the second ray is passing through the F1, so it will be parallel to the principal axis. You just have to check where are they intersecting after refraction. Wherever they intersect, okay, let me just erase the remaining part. Wherever they intersect, from that intersection point, from here, you will have to draw, let me even remove this. You will have to draw a straight line towards like this. From the principal axis, draw an arrow which will come and meet at this intersecting point. Okay, it will also have an arrow. So it's coming downwards. This arrow is coming downward from the principal axis to the point of intersection. So as it's coming downward, you can see downward means it is inverted. An inverted image is what you will get. And because the rays are actually meeting, it is real. So it is always valid. You don't should have any doubt in this. Real images are always inverted. First of all, we can see rays are actually meeting. Yes, that is real. And when they meet, you try to draw a straight line to the point of intersection where they are meeting. Okay, let me use a different color to avoid confusion. So this pink one. It's a straight line coming from principal axis meeting the center, the point of intersection. You see it is downward. The arrow is downward means it is inverted. So this is the first case that we have for the diagram. Anyone has any question for this particular diagram? The first case, any doubt you can ask. Yes, anyone? Okay. At the same time, all the 1-2 mark question also we will cover simultaneously. So convex lens we are taking. Where do we use it? We can use it in the magnifying glass, or that's also called as the burning glass. You can use it. So what is the use of it? Burning glass. From the word itself, what do you think is the purpose of this glass? Camera glass, burning glass, camera lens, you should write. These are the places where we are using the convex lens. Can you tell me where is this burning glass used? Anyone? Yes, Adit. Have you heard about this term burning glass?
No.
Okay, Anushka, Nidhi,
No, ma'am.
yes, Michelle, Vishal. Yes, no one. It's one of the basic idea behind solar cooker, solar water heater. So it tries to focuses the sun's rays. Okay, like long time before itself, people were using it for burning substances, or if they want to, capture the heat energy of the solar. So when light comes, light is never coming just with the light energy. It is also carrying the heat energy along with it, right? So we just want to trap that heat energy. So which lens will be required there? It will be the convex lens. So very olden times, burning glass used to look like this. I'll just show it to you all. This is an old time burning glass, which nowadays also you can try if you have magnifying glass in any of your compass set. What you can do only during the sunny days you can try. Nowadays the weather is very unpredictable. It's raining. If it is sunny anytime, what you can do, take a magnifying glass, keep anywhere outside. Okay, take a piece of paper and white paper or any dark paper is also fine, and try to focus. There will be always some um, lens effect that you will be able to see on the paper. A white color spot you will be able to see. Okay, try to keep the magnifying glass for a long time. Okay, the rays will be falling on it, and convex lens tries to always converge this, try to focus it on one point, and you will see naturally without using any matchstick and nothing, this paper will start burning. I think a lot of children or a lot of us must have done that during childhood. If not, you can try this. So that is the same glass, it's the magnifying glass, or this is how the olden time glasses were. This is shortly called as burning glass because the purpose of it was to burn substances and by trapping the sun's heat. So you can see all the lines were focused towards a point. That's why it's also called as converging lens. Convex lens is called as converging because it converges all the light that falls on it. Whatever light is falling on it, it will try to bring it to a common point, converge it to a common point. So even in the camera lens that we use is where we are using the, so these are the two things you can remember. Sometimes what they ask you is you have to name the lens used in camera lens or name the lens which is used in burning glass or magnifying glass. So you have to remember it is the convex lens. Okay. I will take one more figure. There are almost 6 cases that we have to do for convex. So we'll take one more. First one is done. Second one we will do. So you have the convex lens, principal axis, F1, 2F1, optical center, F2, 2F2. Okay, these are your fixed markings you will do. Now we are going to make the second case. So you all can draw this once the diagram. Markings you can do with pencil because if you're doing rough, you can do the adjustment later. Then from the third case onwards, I will tell you how to do with correct measurements. So second case is we are going to keep the object little behind the 2F2. So somewhere on this path, see if it is not on the principal axis, you have kept your object little on this side, that means it is at infinity. If you take the same object, keep it on the principal axis. Okay, keep it on the principal axis, you will get different position. So now, right now, it is not exactly a 2F1. It is little to the left side. So you call this position as beyond C1. Later, you will have a case, you will keep it exactly at C1. Then you will keep it between C1 and F1. There are these many cases we are going to take. Then we will keep it exactly at F1. And then the last case will be you will keep it between F1 and the optical center. So every time you're going to shift your object little close to the lens. So right now the second case is not, it's not on the C1, it is behind it. So the term you're going to use, case number 2, you can write. Case 2 is object is kept beyond C1 and sometimes you can also refer that as 2F1. Yes, done writing the case and the diagram, then we can focus on the two rays. Ready everyone? Just erasing this because we need to trace the diagram. Okay, So we have this ray. You have to minimum, as I said, minimum two rays are required. So I'm going to take one ray which will come from the head of that arrow, and I will take it parallel to the principal axis. I can also make it pass through focus, but that I will take as the second ray. So first ray, I will make it pass through, not pass through, but parallel to the principal axis. Okay, so the red ray, you can see that the first incident ray parallel to the principal axis. Anushka, tell me, where should it get refracted? Should it go straight? Should it get away? Should it get bent or undeviated? What is the situation?
It should pass through F2.
Yes, it should pass through F2. So it will hit and pass through F2. Then the second ray I'm going to take will pass through the optical center. Ansh, tell me, if it is passing through optical center, where should it go through F2? Should it go undeviated? Or how should it pass? Okay, Nidhi answer the same question. I make it pass through optical center.
It'll go it'll go undeviated.
Yes, correct. It will go undeviated. Okay, so it looks something like this. Okay, where are they meeting? On the top portion or the bottom portion of the principal axis? You all can see it's to the bottom portion. Bottom portion means they are intersecting here, means they are always inverted. Okay, so they are going to be inverted. So if you're doing with correct measurements, if I'm marking 2F2 here, this is the point they have got intersected. So draw a line which will come from the principal axis and meet at this point of intersection. Okay. Now each one of you will give me the points that we are supposed to write. That is object position, image position, size, and nature. Okay. Michelle, tell me the first one, object position. Instead of writing that big term position of object, you can shortly also write that as object position. Where is the object placed?
Beyond the center.
Beyond C1. Okay, specify it is 1, 2, or instead of C1, you can also write 2F1. They mean the same. Okay, Nidhi, tell me the second point. What is the second point? What is the second point you should write? Image position. Anushka, tell me, where is the image formed? What are the 2 points that is valid? F2 and 2F2. So where is the image formed? Between.
Between F2 and
Correct.
2F2.
Correct. Between F2 and 2F2. In place of 2F2, you can also write C2. Okay. Then, Rachel, tell me what is the nature of the image?
Ma'am, real and inverted.
Yes, it is real and inverted. Okay, Adit, tell me the size of the image.
Um, uh, Diminished.
Okay, yes, when you do it with proper measurement, you get a clear idea. This is just rough figure, so it may look almost same, but the size is diminished. So what you will write the size of the image is diminished. It's not highly diminished. You can still see the image. You can still see it. So you can't write highly diminished. You just write diminished. Done writing, everyone? So every time you do ray diagrams, make sure you're going to write all the 4 points. finish writing, everybody? Just quickly going to take one yesterday's presentation where you could just check all the things we are doing is valid. Okay, so first case that we had taken was, see left side is, everyone is able to see the screen. So we're taking it. Okay, we can also have the principal axis. Second points are also taken, too much of lines. Okay. The infinity is not given as a choice now. But so if I bring it anywhere here, so you can see that, see if I take the object to the bottom, I'll get the image on the top. But all the questions we are doing from our textbook is like object is kept on that principal axis. We can change it and we can use an arrow because that's what we are doing. So if I keep it on the left side, so where do you see? You see that the image is formed at the bottom. Here is the object, here is the image. This is image and this is the object. And the size of the object and size of the image, you can clearly see the image is smaller. So you will write diminished in that case. Okay, and you can always work. Now, if I just tell you that I am not changing the position of the object is there, but I work on with the radius of curvature, I can always shift it for my image purpose. So the yellow dots that you see on the principal axis, that's the radius of curvature. So the two dots that you see is technically the C point. Okay, and we can always work with thickness, I mean the length of the lenses. So we have taken the case, and that case is this one. Here, how many rays did they use? 3 rays. You can use 2 rays minimum because 2 rays is what is there for your syllabus. You can take more than that as well. Okay, so you will see that whenever you work with this, like if actually use an, let's take a penguin image. If I bring closer, the image is going far and it is inverted, but it is becoming very big. There will be a time where I go it, make it cross this point. And this is the last case we will see where the object and image are on the same side, but yes, the image is much bigger than the object. Okay, so in the next lecture, Wednesday's lecture, the remaining 4 cases of convex lens, we're going to take any time in between. If I get any free period, I will help you all to do with measurements. I'll tell you how to draw the convex lens on and the concave lens and keep it ready so that when we take it on Wednesday, we can directly start with the diagrams. And when you do with measurements, you will actually get the proper results. Roughly when you do, you are just trying to do the managing. But when you do it with measurement, you will get the correct values. Okay, so we will meet for maths class tomorrow and then